Okay, so now we're going to look at a specific example of a discrete probability distribution known as the binomial distribution. To be a binomial distribution, the experiment must be a binomial experiment. The binomial experiment is recognized by several different conditions that must hold. The experiment needs to be repeated a fixed number of times, and each trial needs to be independent of the other trials. For example, if we're going to toss a coin 20 times, a fixed number of times, and each of those tosses is independent. Whether my first toss lands on heads has no effect on whether toss 2 lands on heads, and so on for toss 3. There can only be 2 possible outcomes of interest, and we're going to call those outcomes a success or a failure. Now notice in the coin toss there are only 2 possible outcomes, heads or tails, so that certainly meets that condition. But now we can take other experiments that have more than 2 possible outcomes. For example, the roll of a die, and then if our outcomes that we're looking for is either it lands on 2 or doesn't land on 2, then it is still binomial because there's only 2 possible outcomes. Each of the probabilities has to be the same for each trial. The probability of tossing a coin and landing on heads is 1/2, and it's 1/2 every time I toss the coin. And I roll the die, there is a 1/6 chance of landing on 2, and it's a 1/6 chance each time I roll the die. So both of those are still meeting all our conditions. And the random variable x must stand for the number of successful trials. In notation, we're going to let n denote the fixed number of times that we repeat the trial. P stands for the probability of a success. Q is the probability of a failure. Notice since there's only 2 possible outcomes, Q is equal to 1 minus P. And X is the number of successes out of n trials. We could see no successes, 1 success, 2 success, all the way up to n successes. So let's look at a couple of examples and try to decide if the experiment is a binomial experiment. And if it is, then we're going to find the values of n, p, q, and list the possible values of our random variable x. Suppose a certain surgical procedure has an 85% chance of success. The doctor performs the procedure on 8 patients. The random variable x represents the number of successful surgeries. Well, first, are we looking at a fixed number of trials? Yes. We're only looking at 8 patients. The probability is constant. It's 85% of a success rate, and it stays constant for each of those patients. The success of a surgery is independent of each other. So, yes, this does represent, each of the surgeries represent a trial, and there's a fixed number of them. There's only 2 possible outcomes, success or failure. The probability of a success is 0.85 for each surgery, and the random variable x stands for the number of successful surgeries. So n is 8, p is 0.85, q is 0.15, which is 1 minus 0.85, and x could be 0, 1, 2, 3, 4, 5, 6, 7, and 8. Now this one we have a jar, and we have 5 red marbles, 9 blue marbles, and 6 green marbles. We randomly select 3 marbles. Is this a binomial experiment? Well, there really are only 2 possible outcomes because we're looking at red or not red. There's a fixed number of trials. We're going to select 3. Our problem comes that each of these trials are not independent of the other because we're doing these draws without replacement. Thus, even though the probability of selecting the marble on the first draw is 5 out of 20, but it doesn't stay 5 out of 20 for each of the draws because without replacement it goes down to 19. There's only 19 marbles in, and so forth. So the trials are not independent, and thus it's not binomial. Now to do the binomial probability formula, it looks a little bit messy here, but let's take it a little bit slowly and see that this is doable. Now, many of you have, even like a TI-30 calculator, has this button usually as a second function. So if you find this button, you can put in this number here, hit the button that looks like this, then put in the number that goes here, hit enter, and you're going to get your calculator calculating this concept for you. But let's see, let me try to explain it to you so you understand what the calculator is doing. N with the exclamation mark is known as n factorial. It stands for n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. For example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 1 factorial is equal to 1, but so is 0 factorial is also equal to 1. And P is the probability of a success raised to the x power, and Q, which remember is the probability of a failure, is raised to the n minus x power. All right, so let's look at an example and see, let's put some numbers in here. So for example, we could do this with drawing a tree and using the multiplication rule, but this only is helpful for very, very small problems, so we're just going to skip over this completely. Now, in our case, n is 3, p is 75% or 3/4, q is 1 minus p, which is 1/4, and x, the number of successes we're looking for out of these 3 surgeries, is 2. So we're looking for c of 3, choose 2, 3/4 squared, 1/4 to the 3 minus 2, which is 1. Now remember, this quantity here stands for 3 factorial over 3 minus 2 factorial times 2 factorial. Remember, 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1, so the 2 times 1's cancel from the top and the bottom, and we're left with 1 factorial, which is 1, and 3 divided by 1 is 3. 3/4 squared is 9/16, 1/4 to the 1 is 1/4, and we get a probability of approximately 0.422. If we want to do a probability distribution, we need to list all the possible values of x with their corresponding probabilities. This takes a little bit of work because we had to do the previous example 3 more times, once for x being 0, once for x being 1, we already did 2, and once for x being 3, and list it out in table form. Let's do another example of constructing a binomial distribution. Suppose we ask 7 adults if they prefer texting because they think it's quicker than calling. In this survey, notice 56% said they prefer texting to calling because it's quicker. Now, n is 7, p is 0.56, q is 0.44, and x could be 0 to 7. We need to do this formula 8 times. Recall, if you try to find in your calculator to see if you have this button, it'll be a C of n, choose x. You would input 7, then do second function C and x, then enter in 0, and then hit the enter button, and you should get 1. Do this 8 times, and then we just list this out in a table, and we have constructed a binomial distribution. And let's do this one more time. For a survey indicates that 41% of women think that say that reading is their favorite leisure time activity. We're going to ask 4 women if reading is their leisure, and we want to find the probability that at least 2 of them say yes. At least 2 means 2 or 3 or 4. Recall from chapter 3 when we're talking about probabilities, and we say the probability of this or that, we add those quantities together. So let's do this. So we're going to find the probability that x is 2, the probability that x is 3, the probability that x is 4, and add them up, this plus this plus this, and we get the probability that at least 2 is approximately 0.542. Since we don't use technology, in this class you'd have to we don't have, I did not make any of these things required, so we're going to skip through this, but you do have a table associated with your book. So let's look at how to use the table. So if about 10% of workers in the U.S. commute to their job by carpooling, let's find the probability that exactly 4 of them. Now there's a mistake on this slide. This probability of a success is 0.10, 10%. And we look at the table, and the probabilities are listed across the top. They're listed in multiples of 5 which 10% is a multiple of 5. So we go down until we see n being 8 and x is 4. Where those two cross, it's 0.005, and that's the probability that exactly 4 of the 8 workers carpool to work. We can also graph, right? And this is the histogram that matches that binomial distribution. We're going to look at the mean, the variance, and the standard deviation. If we know that the probability distribution is a binomial probability distribution, we do not have to use that very messy formula that we did in section 4.1. And it turns out the mean of a binomial distribution is just n times p. The variance is n times p times q. And the standard deviation is the square root of the variance. So suppose in Pittsburgh, 56% of the days in the year are cloudy. Let's find the mean, the variance, and the standard deviation. So in this case, there are 30 days in June, so n is 30. P is the probability of a cloudy day is 0.56, and Q is the probability of a not cloudy day, which is 1 minus 0.56. The mean then is 30 to n times P, which is 16.8. So about an average of 16.8 days are cloudy in June. The variance is n times p times q. 30 times 0.56 times 0.44 is approximately 7.4. And the standard deviation is the square root of 7.4, or approximately 2.7. Thus, on average, there are about 16.8 cloudy days in the month of June, and the standard deviation is about 2.7. Recall from Chapter 2, we consider a value to be unusual if it is more than 2 standard deviations from the mean. So 16.8 minus 2 times 2.7, which is 11.4, and 16.8 plus 2.27 is 22.2. So it would be unusual for Pittsburgh to have 11 or fewer cloudy days, and it would be unusual for Pittsburgh to have 23 or more cloudy days in June. That is the end of section 4.2. Now you go to the My Math Lab, which you find at the Course Compass website, and do homework for section 4.2.